Welcome back to the second section of Chapter 7, where we are going to look at inverses of relations and functions. We saw a bit of this today during the calculator lab. Without looking at any of the math behind it, what is it, anything like that, we're able to see inverses on our graph and make some conjectures. Hopefully during this activity, or during this lesson, you will have your conjectures verified. If not, hopefully you'll learn something in what the conjecture should have been. So, first we have our learning targets. First one, I can recognize and graph inverses of relations and functions. So that's both graph them and be able to recognize them probably from the graph. That's what we were looking at yesterday, or earlier today. And I can find inverses of functions. This is something that we didn't do during the calculator lab. The calculator was able to graph it for us without ever us having to find it, but finding them will be very important. So, first let's look at inverses of relations. Remember, a relation is just a collection of ordered pairs, x and y. X goes to this, y, x goes to y, x goes to y. We don't need to worry about an equation here. That will be taken care of with functions. So, first, we're just going to look at this table. We have x, y, x equals -4, -2, 0, 2, and 4, y equals -2, -1, 0, 1, and 2. In this case, you can probably see a pretty clear linear relationship here. That's fine. We don't care that it's a linear relationship. We're just looking at the points right now. So, to find the inverse of this relation, we only need to do a little thing. An inverse literally switches the input and the output. In a relation, the input is x, the output is y. So in order to find the inverse, we just need to switch x and y. So we can do that. Now all of a sudden, this -2, -1, 0, 1, and 2 is our x column, and y will equal -4, -2, 0, 2, and 4. All that happened is we changed how the rows are labeled, and we have our inverse. Sometimes it's easier, especially when you're starting, to actually rewrite them because you're used to x then y. But if you're paying attention, we're going to be graphing. To graph the inverse, it'll just be -2, comma -4, -1, comma -2. Again, if you really want to write the table again because that's going to help you, go for it. So let's graph. Let's start by graphing the original relation. That would be x on top, y on bottom. So we have the point -4, -2, -2, -1, 0, 0, 2, 1, and 4, 2. So we can get those points in our graph. And then technically in the relation, these are the only 5 points that we know. Graphing the inverse, so we can see the shape, let's connect the dots. The connecting isn't actually part of the relation, but again, it'll help us to see the shape and the relationship between the relation and its inverse. So we have this, it's a straight line, kind of like we thought. Now, graph the inverse. Here we have x on bottom, y on top. So we have the point -2, -4, -1, -2, 0, 0, 1, 2, and 2, 4. So we can graph those points and connect those with a straight line. And this should look kind of like what your graphs earlier today looked like on your calculator, at least as far as the relationship goes. One of your conjectures is, what is the relationship? And not only that, but it had you put another line. It had you put the line y equals x on there. So let's add the line y equals x. Just put it as a dotted line because it's not actually part of what we're doing. Looking at this, the relationship between the relation and its inverse is it's a reflection across this line y equals x. That is how you can tell if it's an inverse by looking at the graph. Is it a reflection across the line y equals x? Here it is. They just go like that. That's really all there is to graphing these. You graph the points, you flip the x and y, graph the points again, and you're done. The other question that these will ask is to look at the domain and range. So the domain is what can x equal, the range is what can y equal. If we start out with the original relation, x was on top. It could equal -4, -2, 0, 2, and 4. So the domain is -2, 4, -2, 0, 2, and 4. The range is what could y equal. In the original relation, it was what was on bottom. And so the range is -2, -1, 0, 1, and 2. Looking at the inverse, it switches the domain and range. The x and y switch, so the domain and range switch. So here, the domain was -4, -2, 0, 2, and 4. That will be the range of the inverse, because that's now what y can equal. And the range will become the domain of the inverse, because that is now what x can equal. When dealing with functions, which won't be today so much, it'll be more later on. I think we'll come back to this topic a bit in chapter 9, looking more at polynomials. And a lot of times it's easier to find the domain of something. So you find the domain of the relation, the domain of the inverse, and that gives you the ranges of each of the other ones. So that switch can be very, very helpful. So looking at this, we found the inverse by switching the x and y. We graphed both of them, found the domain and range, and that's all we did with relations. So why don't you try one? Let's look at x, y. X is -1, 2, 3, 5. Y is 1, 3, 5, and 5. Find the inverse relation, graph both of them, look for that symmetry, and find the domain and range of both of them. This should really only take a minute or so. So go ahead and pause this and come back when you're ready. Easy? Hopefully. Well, let's take a look. First of all, find the inverse. Just switch x and y. That's all that happens. Hey, look, there's our inverse. Yay. Now graph it. So graph the original one. This would be x on top, y on bottom. So we have -1, 1, 2, 3, 3, 5, and 5, 5. So we can graph those, and then we can connect the dots. Notice this one doesn't have a nice linear relationship, but that's okay. Connect the dots. Then graph the inverse. So here we're going to have 1, -1, 3, 2, 5, 3, and 5, 5. So we can put the dots there, connect them so we can see the shape a little bit better. Does this look like it's going to have a reflection across line y equals x? It sure does. It's a nice reflection. And sometimes this is easier to see than the linear ones because, well, lines are boring. This one's a little bit more exciting. You can see that reflection better. Domain and range. First, the relation. Domain would be the top row. Range would be the bottom row. And notice it has 5 twice. We only need to write it once. Range is what could y equal. Y could equal 1, 3, or 5. And then same thing when it's going to be the domain for the inverse. But the domain becomes the range becomes the domain, and we're done with this part. We still have to look at functions. So, telling if it's going to be inverses from a table is do the x's and y's switch. From a graph, is it reflected across the line y equals x? And that's it for this part. So now let's look at functions. Oh, bummer. Hey, you're going to try a couple down here at the bottom. That's okay. These are actually pretty easy. Before we look to see how to find inverses of functions, let's look at some notation. So, the inverse of a function f of x is going to be written as f to the negative 1 of x. That negative 1 exponent means inverse. When we're looking at numbers, 2 to the negative 1 is 1/2. That's the multiplicative inverse of 2. We have an x to the negative 1 button on our calculators that puts the negative 1 in the exponent. Hey, it gives us the reciprocal. When we were dealing with matrices, matrix A to the negative 1 gave us the inverse of matrix A. We already saw inverses back then. We found them a bit differently with matrices. It's way easier with functions, especially the ones you're going to be working with today, because you're pretty much going to be working with lines today. So let's see how we can do this. Start out with f of x equals 0.825x. The first step in finding an inverse, when it looks like this, f of x equals, we'll look at one where it's not f of x and x later, but when it's f of x equals something, first step, change the f of x to y. It means the same thing, and the y is going to be easier to do with the next step. Ends up being less confusing, because the next step, we're going to find the inverse. Remember back with the table, we found the inverse by switching the x and the y? That's exactly what we're going to do here. We're just going to switch the x and the y. All the y's become x's. All the x's become y's. So we have x equals 0.825y. Well, we don't like our functions to look like x equals. We like them to look like y equals. So now that we've flipped the x and y, we just need to solve for y. Well, right now we have 0.825 times y. We need to divide by 0.825. So y equals x divided by 0.825. And then finally, change it back into function notation. It started in function notation, it needs to end in function notation. But now we don't have f of x anymore. We have the inverse of f of x. We have f to the negative 1 of x equals x over 0.825. Let's look at another one. And some of the issues people come up with is they try to do shortcuts. They see, oh, it's just times 0.825, so we're just going to make it divided by 0.825. That'll work in a really easy problem, but here, people make mistakes. If you were to do that right now, you'd say, all right, so this is going to be 5/4 times x plus 15. And that would be wrong. And we'll see why. So first step, change it to a y. And then we're going to switch our x and our y's. And now we need to solve for y. The first step in solving for y is going to be multiplying by this by the reciprocal here. We're going to multiply by 5/4, which would be the same as dividing by 4/5. So we're going to end up with 5/4 x equals y minus 15. Then we're going to add 15 to get y equals 5/4 x plus 15. Notice the parentheses here went away. If you try to do just a shortcut, chances are those parentheses are still going to be there, and that's not going to be the right answer. Finally, change it back into function notation to get f to the negative 1 of x equals 5/4 x plus 15. And so you might be wondering, why find inverses? What is it about finding inverses? Why is this important? Well, it's going to be important coming up next week when we're going to be finding inverses of exponential functions, because that's how we're going to be able to solve an exponential function. But even before that, an inverse switches the input and output values, and so it allows us to simplify things. Instead of having to do all the steps over and over and over again, we can do them once and then plug stuff in. An example, let's say you are doing a science project and you have to collect a whole bunch of temperatures. And you get through about 200 temperature collections, and which might seem like a lot of data points. In real science experiments, 200 data points is not that big of a deal. But let's just say you got your 200 points and you recorded them all, and it was how warm it is outside for the past 200 days, and it's like 60 degrees, well, past couple days, 20 degrees, -5 degrees, -42 degrees, all in Fahrenheit. It wasn't actually that cold, but it sure felt like it. Well, let's say you then looked at the directions, and it turns out you didn't read the directions very well. Purely hypothetical. You look at the directions, it says, find all of your temperatures in degrees Celsius, because you're in a science class. Well, you know that Fahrenheit is going to equal 9/5 times the Celsius temperature plus 32. And so you could plug your degrees in and solve for Celsius. Or you can find the inverse function, put it into a calculator, and have the calculator change your 200 data points for you. I would prefer doing it that way, but I like doing things the easy way. So maybe you want to go through and find them all by hand. That's great. But that's what it'll do. We'll be able to plug in our Fahrenheit data and get out Celsius data. So this is the problem that's just a little bit different, because it's not f of x equals x. In the f of x equals x's, they don't really have meaning, aside from input and output. Here they have meaning. F is Fahrenheit. C is Celsius. If we flip the F and the C would now stand for degrees Fahrenheit, and F would stand for degrees Celsius. And that gets confusing. And in addition to that, does it really matter in our equation if we have F equals something or C equals something? Not really. They're just both letters. So when your variables actually have meaning, don't switch them. Just solve for the other one. We're just going to find an equation that's going to be C equals something. So first step, we have to subtract the 32. And then we have to multiply by the reciprocal, 5/9. We're going to end up multiplying it to the whole side, so let's get some parentheses. And we get our degrees Celsius will be the degrees that we collected minus 32 times 5/9. You can plug that into a calculator, and chances are if you're collecting 200 data points, it's all in Excel. You can run a formula and get those 200 points converted in the matter of a couple seconds. So this is the inverse. Notice we don't need to worry about a -1 or anything, because it's just the opposite conversion. Anytime you have conversion equations, you can go the opposite way and that's the inverse. So, almost done. Real quick, try a couple. Let's try f of x equals x minus 1 3/4. One's going to be pretty easy. You might already know what it is. And f of x equals 21 minus 32x. A two-stepper. This problem and this problem are really as hard. Well, this problem, if you want to consider that one too. These are really as hard as these problems get today. So it should be pretty easy. So anyway, if you haven't finished this already, go ahead, pause the video, and come back when you're done. Did you get it? So, first steps. First step, we want to change the f of x to y. Second step, the x's and the y's flip. So now we have x equals y minus 1 3/4. X equals 21 minus 32y. Now we're going to solve for y. In this one, we just need to add the 1 3/4. And we get x plus 1 3/4 equals y. Change it back to function notation. F inverse of x equals x plus 1 3/4. Over here, first step, subtract 21. Then we're going to divide by negative 32. Notice the negative is part of the denominator. It could be moved out front. If you put it on top, you'd have to flip the things. It would be 21 minus x, because it would have to distribute to both of those. So it works either way. But anyway, we have x minus 21 over negative 32 equals y. Change it back to function notation, and we get that. And so that is section 2. It's about inverses. There's some computations here, but it's more conceptual, because really these computations are going to be pretty basic. So I hope you enjoyed, and I look forward to seeing you in class. Be ready to do a little activity, and don't forget to comment.